Gamma ray bursts are intense flashes of gamma rays, the highest energy form of light. They can last from a few milliseconds to several hours, but most commonly, they last a few seconds to minutes. GRBs are so powerful that they can outshine entire galaxies during their brief existence. Two types of gamma ray bursts. There are two main types of GRBs based on their duration. Short GRBs last less than 2 seconds and are thought to originate from the merger of binary neutron stars or a neutron star and a black hole. Long GRBs last more than 2 seconds and are typically associated with the collapse of massive stars into black holes, often accompanied by supernovae. 3. Formation mechanisms. The formation of GRBs involves extremely energetic processes. Long GRBs, these are believed to occur when a massive star exhausts its nuclear fuel and its core collapses into a black hole. The collapse generates jets of particles moving at nearly the speed of light, which emit gamma rays as they interact with surrounding material. Short GRBs, these are thought to result from the collision and merger of two neutron stars or a neutron star and a black hole. The merger produces a burst of gamma rays followed by an afterglow at longer wavelengths. 4. Afterglow. After the initial burst of gamma rays, GRBs are often followed by an afterglow that can last from days to weeks. This afterglow is emitted at longer wavelengths, including X-rays, ultraviolet, optical, infrared, and radio waves. The afterglow provides valuable information about the environment around the burst and the mechanisms driving the explosion. 5. Energy and luminosity. GRBs are incredibly energetic. A typical burst can release as much energy in a few seconds as the Sun will emit over its entire 10-billion-year lifetime. This immense energy output makes GRBs the most luminous electromagnetic event since the Big Bang. 6. Detection and observation. GRBs were first detected in 1967 by the Vela satellites, which were designed to monitor nuclear explosions. Since then, numerous satellites and ground-based observatories have been used to study GRBs, including NASA's SWIFT and FEMI missions. These observations have helped astronomers pinpoint the locations of GRBs and study their afterglows in detail. 7. Impact on Earth. While all observed GRBs have originated outside the Milky Way, a GRB occurring within our galaxy and directed towards Earth could potentially cause significant damage to the atmosphere and lead to mass extinction events. Some researchers hypothesize that a GRB might have contributed to the late Ordovician mass extinction. 8. Its scientific importance. Studying GRBs helps scientists understand the most extreme physical processes in the universe. They provide insights into the formation of black holes, the behavior of matter under extreme conditions, and the evolution of galaxies. GRBs also serve as probes for studying the early universe, as their immense brightness allows them to be observed from great distances. Gamma ray bursts remain a fascinating and active area of research in astrophysics, with new discoveries continually enhancing our understanding of these extraordinary cosmic events. The afterglow in gamma ray bursts, GRBs, is caused by the interaction of the relativistic jets produced during the burst with the surrounding interstellar medium. 1. Relativistic jets. When a GRB occurs, it emits highly energetic jets of particles moving at nearly the speed of light. These jets are extremely focused and narrow, and they carry a tremendous amount of energy. 2. Shockwaves. As these jets travel through space, they collide with the interstellar medium, the gas and dust between stars. This collision generates shockwaves, similar to the sonic boom produced by a supersonic aircraft. There are two types of shockwaves involved. Forward shock. This shockwave moves outward into the interstellar medium, heating it up and accelerating particles. Reverse shock. This shockwave travels back into the jet itself, further energizing the particles within the jet. 3. Synchrotron radiation. The particles accelerated by these shockwaves emit radiation across the electromagnetic spectrum through a process called synchrotron radiation. This occurs when charged particles, such as electrons, spiral around magnetic field lines at relativistic speeds. The radiation produced spans a wide range of wavelengths, from X-rays to radio waves. 4. Decay of the afterglow. The afterglow gradually fades over time as the energy of the shock waves dissipates and the relativistic jets slow down. The brightness and duration of the afterglow depend on several factors, including the density of the interstellar medium, the energy of the initial burst, and the angle at which the jets are observed. 5. Multi-wavelength observations. The afterglow can be observed in multiple wavelengths, X-rays, typically detected first, as they are produced by the highest energy particles. Optical and ultraviolet follow the X-rays, providing visible light that can be observed with telescopes. Infrared and radio waves detected later, as the afterglow continues to expand and cool. 6. Scientific insights. Studying the afterglow of GRBs provides valuable information about the environment around the burst, the properties of the relativistic jets, and the mechanisms driving the explosion. It also helps astronomers pinpoint the location of the GRB and understand the conditions in distant galaxies. The afterglow is a crucial aspect of GRBs, offering a wealth of data that helps scientists unravel the mysteries of these powerful cosmic events. Ultraviolet, UV. After the initial burst, the afterglow can emit ultraviolet radiation. UV observations help in understanding the properties of the burst and the surrounding environment, as well as the redshift, which indicates the distance of the GRB. 2. Infrared, IR. Infrared observations are crucial, especially for GRBs that occur in dusty regions where visible light might be obscured. IR afterglows can provide information about the dust and gas in the host galaxy and help in detecting GRBs at higher redshifts. 3. Radio waves. Radio afterglows are typically detected days to weeks after the initial burst. They provide insights into the density of the interstellar medium and the energy of the explosion. Radio observations can also help in pinpointing the exact location of the GRB. 4. Gamma rays. In addition to the initial burst, some GRBs exhibit extended emission in gamma rays, which can last for several minutes to hours. This extended emission provides clues about the central engine driving the burst. 5. Multi-wavelength observations. Observing the afterglow in multiple wavelengths is essential for a comprehensive understanding of GRBs. Each wavelength provides different pieces of information. X-rays reveal the high-energy processes and the immediate environment of the burst. Optical and UV help in determining the redshift and studying the host galaxy. Infrared, useful for detecting GRBs in dusty regions and at high redshifts. Radio provide information about the interstellar medium and the energy of the explosion. 6. Scientific instruments. Various space-based and ground-based telescopes are used to observe GRB afterglows across these wavelengths. For example, Swift Observatory detects X-ray, UV, and optical afterglows. Fermi Gamma Ray Space Telescope observes gamma rays. ALMA Atacama Large Millimeter/Submillimeter Array detects radio afterglows. By studying afterglows in different wavelengths, astronomers can piece together a more complete picture of the GRB event, from the initial explosion to the interaction with the surrounding environment. Initial detection and localization. When a GRB is detected, satellites like NASA's Swift and Fermi provide an initial localization of the burst. This localization is often accurate to within a few arc minutes, which is a relatively large area in the sky. 2. Follow-up observations. To pinpoint the exact location, astronomers conduct follow-up observations using ground-based telescopes. These observations focus on the afterglow of the GRB, which can be detected in X-rays, optical, infrared, and radio wavelengths. The afterglow provides a more precise position, often within a few arcseconds. 3. Identifying the host galaxy. Once the afterglow position is known, astronomers search for a galaxy at that location. This involves optical and infrared imaging. High-resolution images are taken using telescopes like the Hubble Space Telescope or large ground-based observatories. These images help identify potential host galaxies near the afterglow position. Spectroscopy. Spectroscopic observations are used to determine the redshift of the afterglow and the candidate host galaxy. The redshift provides information about the distance to the GRB and confirms whether the galaxy is at the same distance as the burst. 4. Association with the host galaxy. To confirm the association between the GRB and the host galaxy, astronomers look for several indicators. Spatial coincidence. The afterglow must be located within or very close to the candidate galaxy. Redshift match. The redshift of the afterglow and the galaxy must match, indicating they are at the same distance. Star formation activity. GRBs are often associated with regions of active star formation, so the presence of such regions in the candidate galaxy supports the association. 5. Multi-wavelength observations. Observations across different wavelengths help build a comprehensive picture of the host galaxy. X-rays and UV provide information about the high-energy environment and star formation rates. Optical and infrared reveal the structure and stellar population of the galaxy. Radio can detect molecular gas and dust, which are important for star formation. 6. Advanced techniques. In some cases, advanced techniques are used to study the host galaxy in more detail. Gravitational lensing. If a GRB is lensed by a foreground galaxy, the lensing effect can magnify the host galaxy, making it easier to study. Deep field surveys, observations of deep fields, such as those conducted by the Hubble Space Telescope, can reveal faint host galaxies that are otherwise difficult to detect. 7. Statistical methods. For GRBs without a clear host galaxy, statistical methods are used to estimate the properties of potential host galaxies based on the observed population of GRB hosts. Faint or distant host galaxies. Some host galaxies might be too faint or distant to be detected with current telescopes. If the host galaxy is very far away, it might be beyond the detection limits of even the most powerful instruments. 2. Dust obscuration. In some cases, the host galaxy might be heavily obscured by dust, making it difficult to observe in optical wavelengths. Infrared observations can sometimes help in these situations, but even then, the galaxy might remain undetected if the dust is too thick. 3. Low luminosity hosts. The host galaxy might be intrinsically low in luminosity, such as a dwarf galaxy. These galaxies are faint and can be easily missed, especially if they are located in regions with bright background light. 4. High redshift GRBs. GRBs occurring at very high redshifts early in the universe's history can have host galaxies that are extremely faint due to the vast distance. These high redshift GRBs are valuable for studying the early universe, but their host galaxies are often challenging to detect. 5. Isolated GRBs. There is a possibility that some GRBs occur in regions of space with very low galaxy density, making it difficult to associate them with a specific host galaxy. These isolated GRBs might be the result of unusual progenitor systems or environments. 6. Observational limitations. Sometimes, the lack of association with a host galaxy can be due to observational limitations. For example, if the afterglow fades too quickly, there might not be enough time to conduct follow-up observations to identify the host galaxy. 7. Statistical methods. In cases where a host galaxy is not detected, astronomers use statistical methods to estimate the properties of potential host galaxies based on the observed population of GRB hosts. These methods can provide insights into the likely characteristics of the undetected host galaxies. Examples of hostless GRBs. There have been several documented cases of GRBs without a clearly identified host galaxy. These cases are often subjects of detailed study to understand the reasons behind the lack of detection and to improve observational techniques. The study of GRBs without associated host galaxies continues to be an important area of research, as it helps astronomers refine their models of GRB progenitors and the environments in which these powerful events occur. Progenitor systems. The absence of a detectable host galaxy can suggest that the progenitor systems of these GRBs might be different from those typically associated with known host galaxies. This could imply isolated progenitors. Some GRBs might originate from isolated stellar systems or regions with very low star density. Unusual progenitors. The progenitors could be unusual or rare types of stars or compact object mergers that do not reside in typical star-forming regions. 2. Galactic environments. Hostless GRBs challenge our understanding of the environments in which these events occur. They might indicate that GRBs can happen in a wider variety of environments than previously thought, including low-density regions. GRBs could occur in regions with very low interstellar medium density, making their host galaxies faint or undetectable. High redshift galaxies. Some hostless GRBs might be associated with very distant, high redshift galaxies that are beyond the detection capabilities of current telescopes. 3. Detection and observation techniques. The study of hostless GRBs highlights the limitations of current observational techniques and the need for advancements in technology. Improved sensitivity. There is a need for more sensitive instruments to detect faint or distant host galaxies. Multi-wavelength observations. Enhanced multi-wavelength observation strategies can help identify host galaxies obscured by dust or located in challenging environments. 4. Cosmic evolution. Hostless GRBs can provide insights into the evolution of the universe, early universe. If some hostless GRBs are from high redshift galaxies, they can offer valuable information about the conditions and processes in the early universe. Star formation. Understanding the environment of hostless GRBs can shed light on star formation and stellar evolution in different cosmic epochs. 5. Theoretical models. The existence of hostless GRBs necessitates revisions and expansions of theoretical models. GRB formation. Models of GRB formation must account for the possibility of progenitors in diverse and atypical environments. Host galaxy properties. The properties and distribution of host galaxies need to be reconsidered to include scenarios where the host is faint or undetectable. 6. Astrophysical implications. Hostless GRBs can influence our understanding of various astrophysical phenomena, black hole formation, insights into the formation of black holes from isolated or unusual progenitors, binary mergers, understanding the conditions under which neutron star or black hole mergers occur outside typical galactic environments. 7. Future research. The study of hostless GRBs encourages future research directions, deep field surveys, conducting deep field surveys to detect faint host galaxies. Advanced telescopes, utilizing next-generation telescopes, such as the James Webb Space Telescope, JWST, to explore the faintest and most distant galaxies. In summary, hostless GRBs challenge existing paradigms and push the boundaries of our understanding of cosmic events. They highlight the need for continued advancements in observational technology and theoretical modeling to fully comprehend the diverse environments in which GRBs can occur. Very high-energy afterglow emission. Recent studies have detected very high-energy (VHE) afterglow emissions from GRBs such as GRB 180720b and GRB 190829. These emissions, observed by the High-Energy Stereoscopic System (HESS), suggest that the afterglow can extend into the VHE gamma-ray range, greater than 100 GeV. This challenges existing models of GRB afterglows and suggests that inverse Compton scattering might play a significant role in producing these high-energy photons. 1. 2. Brightest GRB ever recorded. GRB 221009, detected on the 9th of October 2022, is the brightest gamma-ray burst ever recorded. This event was so intense that it disrupted the normal functioning of many gamma-ray telescopes. The joint analysis of data from the CHMC and FEMI/GBM instruments revealed unprecedented gamma-ray lines up to 37 MeV, the highest energy gamma-ray lines seen from any celestial object. This discovery provides deeper insights into the physics of GRBs and the mechanisms driving these powerful explosions. 2. 3. Search for hostless short GRBs. A recent study focused on searching for hostless short GRBs using large aperture telescopes. This research aims to identify and understand short GRBs that do not have an associated host galaxy. The findings from this study could help refine our understanding of the environments and progenitor systems of short GRBs, which are often linked to the mergers of compact objects like neutron stars. 3. These discoveries highlight the ongoing efforts to understand the nature and origins of hostless GRBs. They also underscore the importance of multi-wavelength observations and advanced detection techniques in uncovering the mysteries of these powerful cosmic events. Atmospheric effects. Ozone layer depletion. The intense gamma radiation from a GRB would interact with the Earth's atmosphere, particularly the ozone layer. This interaction would produce nitrogen oxides, NOx, which can catalytically destroy ozone molecules. The depletion of the ozone layer would significantly reduce its ability to block harmful ultraviolet (UV) radiation from the sun. 1. Increased UV radiation. With the ozone layer compromised, more UVB radiation would reach the Earth's surface. This increase in UV radiation could have severe biological effects, including increased rates of skin cancer, cataracts, and other health issues in humans, as well as detrimental effects on wildlife and ecosystems. 1. 2. Biological impacts. DNA damage. Gamma radiation and increased UV radiation can cause direct damage to DNA in living organisms. This damage can lead to mutations, cancer, and cell death. The high-energy photons from a GRB would be particularly effective at breaking chemical bonds in DNA molecules. 2. Mass extinctions. The combined effects of radiation and environmental changes could trigger mass extinction events. Some researchers hypothesize that past mass extinctions on Earth, such as the late Ordovician extinction, might have been influenced by GRBs. 1. 3. Climatic changes. Atmospheric chemistry alterations. The introduction of large amounts of NOx and other reactive species into the atmosphere could alter its chemical composition. These changes could affect climate patterns and lead to phenomena such as acid rain. 3. Cooling effect. The destruction of the ozone layer and the subsequent increase in UV radiation could also lead to a cooling effect on the Earth's surface. This is because the increased UV radiation can lead to the formation of aerosols that reflect sunlight away from the Earth. 3. 4. Impact on technology and infrastructure. Satellite damage. Satellites in orbit around Earth would be exposed to intense gamma radiation, potentially damaging their electronics and disrupting communications and navigation systems. 4. Power grids. The ionizing radiation from a GRB could induce currents in power lines and other electrical infrastructure, potentially causing widespread power outages and damage to electrical systems. 4. 5. Geophysical effects. Ionospheric disturbances. The ionosphere, a layer of the Earth's atmosphere that contains a high concentration of ions and free electrons, would be significantly disturbed by the gamma radiation. This could affect radio communications and GPS signals. 4. Lightning and weather patterns. Changes in the ionosphere and atmospheric chemistry could also influence weather patterns and increase the frequency and intensity of lightning storms. 4. 6. Historical context and research. Past events. While no GRB has been directly observed to impact Earth, there is evidence suggesting that such events have occurred in the past. For example, the GRB 221009, detected in 2022, was the brightest ever recorded and caused measurable disturbances in Earth's ionosphere. 5. Ongoing research. Scientists continue to study GRBs and their potential impact on Earth. This research includes monitoring for GRBs, modeling their effects on the atmosphere and biosphere, and developing strategies to mitigate their impacts. 5. 7. Probability and preparedness. Likelihood. The probability of a GRB occurring close enough to Earth to cause significant damage is relatively low. GRBs are rare events, and most occur in distant galaxies. 5. Preparedness. Despite the low probability, understanding the potential impacts of GRBs is important for planetary defense and preparedness. This includes improving our ability to detect and study GRBs and developing strategies to protect Earth's atmosphere and biosphere. 5. In summary, while the likelihood of a GRB directly impacting Earth is low, the potential consequences are severe. Continued research and monitoring are essential to better understand these powerful cosmic events and to develop strategies to mitigate their impacts. That was all. Goodbye.